Hey everybody, before we get into the calculations of the independent sample's t-value, it's important that we talk about something called the assumptions of the test. So let's get going there. Any statistical test is really just kind of like a calculator in that it's an equation. You put in some numbers and it does its thing and then it pumps out a result. And that's kind of it, but it does nothing to ensure that you made the correct choices in deciding what numbers to put in, for example. Now that probably doesn't make a lot of sense right now, but let's use an analogy with something that should help. I like to use the analogy of a washing machine. A washing machine has several settings on it based on the types of clothes that you're going to put in. For example, there's gentle cycle. You could put it on hot water, cold water. You could pre-soak and things like that. And for different kinds of clothing, different settings on the machine are appropriate. Now, if you mess up those settings on the machine doesn't say, wait a second, this is wrong. You're not supposed to use these settings for that item of clothing. What you do then is risk ruining that item of clothing or doing something bad to it. So it's very like that with statistical tests. Every one of those settings on the washing machine is kind of like a different statistical test. And just like the machine doesn't know if it's appropriate for that item of clothing, the statistical test itself doesn't know if it's appropriate for the data that you're putting into it. You're the one who's responsible for doing that. So it's very important that researchers are aware of the appropriate circumstances in which to use a test versus another test. So you need to be very aware of how you gathered your data and what this kind of test actually assumes to be true. And then you need to test whether those things are actually true of the test. So that's what we're going to cover today for the independent samples t-test, although every test has some assumptions. The independent samples t-test assumes three things to be true. We'll talk about each of these individually a little bit more, but the first is that the groups are independent of each other. The second is that their distributions are relatively normal, like a bell-shaped curve. And the third assumption is that the standard deviations are relatively similar to each other. A very fancy way of saying that is homogeneity of variance, which just means the variance is roughly equal to each other. But we'll talk about this in just a minute, and also what you can do if these are not met, for example. So as the name implies, the independent samples t-test assumes that the groups are actually independent of each other. The samples from which you drew your data are actually independent of each other. If you're not sure about this, we talked about this, I believe it was the last lecture where we talked about the difference between dependent samples and independent samples. So you can review that a little bit. But of course, the problem here is that if there's a reason to believe that people in one of the groups did depend on people in one of the other groups, now you're probably running the wrong test. In fact, an independent samples t-test would not be the appropriate equation at all. You should probably redesign your study a little bit, maybe, and the way that you input your data. You may need to match people, for example, to make a matched samples t-test. Okay, so it's very important that you explore this. Even if it's not your design to see if they're dependent, you can ask people to see if there's any reason to believe that the observations are dependent. For example, you could ask participants. You could say, hey, are you related to anybody else in the study? Do you live with anybody in this study? Who's also partaking in the study? Are you married to anybody who's in the study? And things like that. Now, it of course depends very much on the actual circumstances. For example, I gave an example of the smoker and secondhand smoke. If they're in the same shared environment, then that probably would not be a very good study. They wouldn't be independent of each other, at least. However, if you wanted to change the design and call them dependent, that would start to make a lot more sense, depending on exactly how you wanted to go about that. Anyway, so the point is the independent samples t-test assumes that the samples are actually independent. If not, you're probably using the wrong test. The second assumption of the independent samples t-test is that both of the distributions of the samples are relatively bell-shaped or normal. Okay, what I'm essentially saying is that there should be very little skew or no skew at all to both of the distributions if you graph them in a histogram. For example, let's take a look at this and see why this is important. Let's say that we took two different samples and we measured them on IQ or something. It doesn't really matter. But let's say that we have one of the distributions that is symmetrical. That's great. Maybe a little leptokurtic, and that's fine. This other one has a positive skew. Now, why is that an issue? Of course, you'll recall that a positive skew means that the mean gets biased by these extreme scores up on the right. And so that mean gets stretched over too far to the right, and now it's no longer maybe a good representative of the actual average of this data set. It isn't a good typical score measure for this blue data set or the group 2 data set. So what that means is now these means look more similar to each other than maybe would be accurate if that's not a good representative. And so what you do then is increase your risk of a type 2 error in this particular scenario because these means look closer together. Now, of course, the opposite would also be true. If this blue distribution, group 2's distribution, had a negative skew, now you would be increasing your chance of a type 1 error or falsely finding that they did differ. Okay, now of course this would all change depending on which one's on which side and what type of skew it is. But that is the risk that we run with a type of skew, is we increase our risk of a type 1 or type 2 error if we're not using the representative measure of central tendency. Now, of course, the issue here is the independent samples t-test uses the means. It doesn't take into account the median or the mode for this particular group. And as we talked about, that may be the more appropriate measure of central tendency for that particular distribution. Then the last assumption of the independent samples t-test is that there's relatively similar standard deviations, okay? What that's essentially getting at is the kurtosis of the distributions. In other words, they're both relatively the same. So again, let's talk about why this may be a problem. If you have one distribution that's relatively, we'll call that a little leptokurtic, and the other that's more platykurtic, now what you have is a real big problem potentially, because the leptokurtic distribution has a relatively precise estimate of the mean. The mean is relatively closer to all of the other data points. In the platykurtic distribution, the mean is a less precise estimate. There's a lot more noise in that distribution. And so therefore, what the t-test concludes may now not necessarily be accurate. Especially the problem is because it pools the standard deviations, or it combines the standard deviations in the equation, as we talked about. Now what's happening is sort of this leptokurtosis is kind of being canceled out by that platykurtosis, and the t-test doesn't know the difference then. But you as the researcher need to be very cautious about this and say, actually, we had a lot more variability in one of those groups and a lot less variability in the other group. That's kind of weird. I don't know why that would be. We should try to figure that out. Now, what can you do in these scenarios? We'll talk about that in just a moment. Well, first, it's important that you actually test for these assumptions. Now, there are some formal tests that you can do, especially for the normality of a distribution. There's some very fancy kind of statistical tests that you can do to see, is my distribution different from normal? That's a little beyond the scope of what we're doing here. So sort of a quick and dirty way of testing this out is you go ahead and graph the data and take a look at it and see, oh, is this skewed? Does it seem like it has a lot of platykurtosis or something like that? Another thing you could do is just calculate the standard deviations and say, for both groups, and say, wow, are these relatively different from each other or roughly the same? And they're not going to be exactly the same, but depending on just how big the scale is that you're using for that dependent variable, the standard deviation should be pretty darn close, I would say. But there are some formal tests, as I said. You can look in the textbook to read a little bit more about that kind of thing. Anyway, but the point is we want to be cautious about this, so we test for those. And let's say that we have violated one of these assumptions. What can you do? One thing that's relatively fancy that you could do is transform your data. For example, if you've got a skewed distribution, sometimes you can multiply each of the values in your data set, or at least that sample, by their natural log. And that sometimes will sort of normalize the distribution in some ways. However, be cautious about that, because that will complicate your interpretations, because now you're no longer interpreting the dependent variable on its original scale. Now it's the natural log you're interpreting, so that can be a little bit tricky. Some statisticians don't like that. Another thing you could do is exclude extreme scores. So if you've got a positively skewed distribution, for example, get rid of some of those scores that are too high until it sort of normals out. Now, again, that risks some other things, because now you're just sort of artificially getting rid of data, and maybe those data are accurate. And so some researchers don't exactly like that. In any case, I would, at a bare minimum, try to understand what's going on. Why would I get a skewed distribution for this variable? Is it some problem with my sampling? Is something going on? Now, if it was a problem with your sampling, now you have a new conversation to have. Do you need to get a new sample? Do you need to even out the sample with some other people? That kind of thing. Now, even if you find these things are violated, these assumptions are violated, and you're not able to fix that, One good thing is that the t-test is known to be robust to violations. So that's a fancy word that just means that it usually is going to make the correct assumption even if one or more assumptions is violated. So that's something that kind of should help you get a little more sleep at night even if you've violated some of these assumptions. So I would recommend try to explain why it's going on, see if you can normalize the data without, causing new problems, and then if not, at a bare minimum, communicate that to your reader or your audience, whoever that is, and thankfully the t-test is probably going to make the correct call anyway. Okay, all right, a quick recap of what we covered today. Every statistical test assumes that there's something true about the way that the data were collected. In other words, it assumes that you are putting in the right laundry with the settings that it has on that machine. So it's very much up to the researcher to know these assumptions and then to check them out before running the statistical test. If you do it wrong, you might ruin that item of clothing, or in statistical terms, you might commit a type 1 or type 2 error, and that's potentially very concerning. Okay, so be very cautious about that, and if you find concerns, you either transform your data, you change something about your test, you recollect data with new circumstances. At a bare minimum, you communicate to your audience anything that was concerning about those assumptions. Okay, and of course the independent samples t-test is usually correct in its call, even if you violated some of those assumptions. So you can rest somewhat easy, even if you didn't get it quite right. Okay, next we will actually calculate an independent samples t-value, and then after that we'll work on interpretation.